we'll move towards the proof of the theorem. Well, almost all the work is contained here in this proposition. So what does the proposition say? It says exactly the same thing that the theorem says, except that it supposes n is a nilpotent operator. And in fact, it doesn't need to assume that the space is complex. If you have a nilpotent operator, you have a Jordan basis. And so what does a Jordan basis of a nilpotent operator look like? What's the Jordan matrix? Or what's the matrix of that operator with respect to that basis? Well, it just is the same as what we saw before, except that the eigenvalues are all equal to 0. Well, the eigenvalues being equal to 0, so on the diagonal we have 0. Below the diagonal we have 0, that we have already for a long time, that we can make an operator like this, but now we're just assuming n is nilpotent. We have already proved that if n is nilpotent, we can make the matrix upper triangular. But now we're going to make it not just upper triangular, we're going to make chains of ones. So it has zeros everywhere except for a few ones just above the diagonal. Where can these ones be? Well, they can be anywhere. Once you have the ones, so here's a 1, here's a 1, it determines a block. The block stops here because here's a 0. Here's a 1, here's a 1. So here's a 1, and here's a 0, so it determines another block. Since here you have a 0, it determines another block. And so on, so on, so on. So here you have a 1, but then you have a 0. So this determines another block, and everything in between. And here there is 1, so this is a block. So it's not that you can only have ones inside the blocks, it's the other way around. You define the blocks so that they are filled with ones in the second diagonal, or in the line just above the main diagonal. So this is the simplest form we can give to a nilpotent operator. And the statement of the proposition is more explicit. It does not talk about matrices. The statement of the proposition says there is a basis for V, and the basis of V is of the following form. There is a vector, then n applied to that vector, n applied to the previous vector, which is the same as n squared applied to the original vector, then n applied to the previous vector, which is the same as n cubed applied to the original vector, and then you keep going until there will be n to some power applied to a vector applied to the original vector. This is one part of the basis. The second part of the basis is another vector. None of these, that's a basis, so this is a new vector, then n applied to it, then n applied to the previous one, and so on, until n applied to the previous one, which is the same as n to some number applied to the original vector here. And you have many other blocks like this until the last block is the same, a vector, n applied to that vector, n applied to the previous vector, n applied to it, and so on until n applied again to the previous vector, which is the same as just applying n a number of times. And so it has a basis of this form, and moreover, if we apply n one more time, so this dj is the number of times you applied n in each of these pieces. If you apply one more time, so here's n plus 1, if you apply one more time, you would get 0. And of course, 0 is not part of the basis. But if you think in terms of a chain, you start with a vector, it's mapped onto another vector, then it's mapped onto another vector, another another vector. The last one is mapped onto 0. So the last one is actually an eigenvector with eigenvalue 0. So it's a vector in the kernel. Okay. And this is what the proposition says. And if the proposition, we can think it stops here. But then once you have a basis that is of this form, it's just a thread that ends at 0, another thread that ends at 0, and another thread that ends at 0. And if they form a basis, then if we write now this basis backwards, if we reverse the order of this basis, and we see what's the matrix that we get. Well, n applied to V1 to the n applied to the last element of the basis will give us the second last element of the basis, which means exactly this is v1. v1 will be the last element of the basis, and when we apply n to it, n v1, that's v2. And now if we apply n to it, if we apply n to v2, we come here and we get v3. That's what we get. And what's the size of this little block here? The size of this little block here is just the number of vectors. And what's the number of vectors? It's v1 plus 1, because we start with 0. This is n to the 0. 1, 2, up to d1. So if we count 0 as well, we have d plus 1 vectors here in this block. Then in the second last block, we get this block here. So the first vector in the block is mapped onto the second vector. No, here is mapped onto the second vector. The second vector is mapped on 0. So we move to the next block. Maybe the next block only has one vector. That happens, yeah? Maybe v3. You have v3, but you don't have n v3. You don't have it because maybe n v3, maybe it equals 0. So you can have this very simple block, yeah? This is a 1 by 1 block with a 0 in it. It's a Jordan block, yeah? Because it has 0 on the diagonal and 1 just above it, except just above it does not exist here. So here's a 0 alone, and you have many of these until the last one here, which is the last one here, but first one when we read the matrix from left to right, is again some vector. When we apply n to that vector, we get, when we apply n to the vector, we get the last vector. When we apply n to it, we get 0. Okay? So I'll let you think a little bit why a chain like this with this property, so that the last one, the last vector of the chain, they're all mapped to 0, so they're all eigenvectors. A chain like this, if we read it backwards, if we read it from right to left, then it will give us a matrix that is exactly like this. And it even has the size of the blocks prescribed like this. So that's a Jordan basis for a very special case, the special case where all the eigenvalues are 0. And this is the main work, this is the hard proposition to prove. Right now, in the next step, we'll just use this proposition to prove the theorem.